things have been a shit show at my place. But anyway. Okay, all right, I'm recording now. So yeah, this week's discussion is going to be somewhat, I guess, expanding on the end of last week's discussion. And then we're also going to do a little bit about adders, which wasn't in previous lecture, I think. It will be, or it wasn't the last lecture briefly, but I think Sophia will continue that for next lecture. All right, so just a quick discussion or like correction from discussion 9 that we saw. Basically, we just want to show you that in the case that like gamma is not equal to 1 and you have the k factor, you start off with the propagation delay of a gate, which is this equation, but then as you go through, you would factor out a gamma here when you go from C in of the inverter to C parasitic of the inverter, right? So then this term becomes your parasitic delay, this is your logical effort, and this is your fan out. And the implication of this is when you calculate the P and the LE factors for various different gates, okay? So in this case, if we start off with a reference inverter, right, that has 1 here for the NMOS and a K here, right? What would be the logical effort and the parasitic delay, right? Logical effort we know for inverter is always, not gamma, is always 1. But what would be the parasitic delay? This would be looking in this way, right?
K plus 1 C in.
Say it again.
So parasitic would be K plus 1 C in, right?
K plus 1, correct, over C in.
Yes.
Right. So what would that factor be? Right.
Wouldn't it be times C in?
No. K plus 1 times C in, you're saying?
Yes, because that would be the parasitic capacitance of the gate.
No, the parasitic capacitance of this gate is actually just going to be gamma times Cn, right? But Cn just so happens to be K plus 1.
Okay, I see.
Right? And then you divide that by Cn and you get a gamma. Does that make sense?
Yeah.
Okay, all right. So let's quickly go through the 2-input NAND example. So 2-input NAND.
But shouldn't the logical effort be K plus 1 for the inverter?
No, because the logical effort, recall, is the input capacitance of the gate over the input capacitance of the inverter. So it's just K plus 1 over K plus 1. That equals 1.
Oh, I see.
Yeah. All right, so let's do 2-input NAND, A and B. These are going to be 2, right? That would be the sizing that you would do. So what would be the logical effort of this? Right. What is the input capacitance of this gate?
K plus 2.
Right, K plus 2. And the input capacitance of an inverter is K plus 1. All right. What about its parasitic capacitance? What do you see looking in here? Okay, you see
2K plus 2.
2K plus 2.
2K plus 2, that's correct. And then that times a gamma, right? And then it'll be over K plus 1. And this equals 2 gamma. Right? And then for a 2-input NOR, this would be 2K, 2K, A, B, B. This size would be a 1, and this would also be a 1. So what is the logical effort of this? I'll just finish it, 2K plus 1 over K plus 1. And the parasitic delay of this is similar to the other one, where you have 2K plus 2 times gamma over k plus 1, which is equal to 2 gamma. All right, so that's just how you would calculate the parasitic and parasitic delay and the logical effort in the case where gamma is not equal to 1 and you have a factor of k. So you can see that the gamma doesn't factor in when you're doing logical effort. It only factors in when you calculate the parasitic delay. So therefore, when you're doing like sizing and whatnot in like a chain, you don't need to worry about gamma. Okay. All right. I think we went over this example last time, so I'm going to skip it for the most part. The other discussion didn't get a chance to go through it. So, all right. So this is an expansion on homework 7's path effort. And what we're going to do in this particular example is to work it out using both the path effort version and an Elmore delay version. Okay. And in the Elmore delay version, we're going to see how you do Elmore delay with like discontinuities that are added by the logic gates. Okay. So if we go the path effort route, what would we do, right? The delay is going to be, again, some, P plus LE times fan out, right? So we're going to do a delay is equal to, tau inverter, okay? And then for the very first gate, we see that the parasitic delay, right, with the gamma of 1.2 is going to be 1.2 plus the logical effort of the inverter, which is 1, right? And then A is 9, right? So the fan out is 9. So 1 times 9. Then for the NAND gate, or sorry, the NOR gate next, you have a 2 gamma as the parasitic delay. So that's 2 times 1.2. And then its logical effort is 1.5, and its fan out is B over A, which is 6.4 over 9. Okay. And then the idea is that you also have branching here. So you have to multiply that by 3, right? This branching here. Okay. So then you have to add the third stage, which is the NAND gate of size B. So that also has 2 gamma of parasitic delay. So that's 2.2 times 1.2 plus its logical effort times fan out, which is going to be 1.5 times 38 over 6.4. You see that? And when we calculate it all out, it comes out to about Tn times 27, right? And then we're going to see how this also works out using Elmore delay. Okay, so in contrast to what you saw with Elmore delay last week, what we're going to do is show that we can do 3 different networks and then calculate the sum of the time constants of each of those 3 networks. And then it should come out to very roughly the same as the path effort. So for the very first network, we have the first stage, which is an inverter, right? So it starts out with some equivalent resistance, and it sees a parasitic capacitance, right, of 1.2 C in, and then it sees a load capacitance from the NAND or NOR gate of the next stage, which would be 9 C in, right? So this is the inverter. Then for the NOR, we have a similar thing, right? Okay, so now the question is, what is this equivalent resistance? So we know that the logical effort of a NOR is 1.5, right? But its input capacitance is 9. That means that the sizing of the NOR gate relative to a unit size NOR gate is actually 6 times, which is equal to the fan out, or its capacitance, input capacitance divided by its logical effort, right? So that means we actually have R equivalent divided by 6 here. Its parasitic capacitance is going to be 6 times 2 gamma C in, and then its output capacitance is going to be 3 times B, which is 6.4 C in, okay? Then we have a NAND, and we also have resistance, capacitance, and then the output here is going to be 38 C in, right? And similar to what we did before, we know that we need to find out what the sizing of this is, right? And we know that the input capacitance is 6.4 and its logical effort is 1.5. So 6.4 divided by 1.5 happens to be about 4.3, right? So this capacitance is going to be 4.3 times 2 gamma. No, let me write that a little more clearly. 4.3 times 2 gamma C in. Okay. Does it make sense how I got those capacitances?
Hey, Harrison.
Yeah.
I thought the Elmore delay was for wires. We could use that for gates as well.
Yes. So recall from last discussion, I said that the resistances in Elmore delay calculation can be from the transistors, the wire resistance, and like any other resistances that you may have. And then all the capacitances can be input capacitance, right? Parasitic capacitance and wire capacitance. And you can build any number of networks out of this and do an Elmore delay calculation. The only thing is that if you have any discontinuity in this network, then you have to treat them all as separate time constants. Does that make sense?
Yeah. Also, do you think you can write like the general form of those formulas that you're using to calculate stuff? Just write it down like as a reference.
Well, I mean, I'm using existing formulas, right? When I'm doing the calculations for the sizing of A and B, I'm just taking the, right, you know that logical effort equals C in gate over C in of an inverter, right? So if the C in of the gate is 9, right? This is 9. And this is, like we need to get 1.5, right? As logical effort. So what is this? So this would have to be 6. That's how you would size it. So I'm not using any new equations here. Does that make sense?
Yeah.
Okay. Great. Okay, so now that I have that, I have 3 different RC networks here. So what I do is I calculate the sum of all these RC networks. So the propagation, the time constant here is going to be equal to the first network. So that's going to be Req times the capacitors that it charges. So 1.2 C in plus 9 C in, right? Then the next network is going to be R equivalent over 6 times its capacitance that it sees, which is 6.2 times gamma C in plus 3.6 times 4 C in. All right? No, 3 times 6.4 C in, because 3 is the branching factor. Okay, and then we have the last network, which is going to be R equivalent over 4.3 times the capacitance it sees, which was 4.3 times 2 gamma C in plus 38 C in, right? And then if we were to do all of this calculation, we would actually get about 27.03 R equivalent C in, which equals 27.03 tau in. So you can see that the Elmore delay is very similar to the path effort type of calculation. Now, obviously, you don't want to do the Elmore delay version when you're just having networks like this, because it is more complicated and you have to back calculate all the sizes of the gates using the logical effort, when instead you could just use path effort to do it all.
I have a question.
Yeah.
So I think for given a technology, we will have the same tau inverter.
Yes.
The given technology, no matter how the size, how you change,
That's
you
right.
have the same.
Yeah, because the
Okay.
unit inverter in a technology would always have a definite equivalent resistance. Now, obviously, the caveat to that is that the REQ is calculated at a specific supply voltage, right? So if you were to scale the supply voltage in that same technology, you would get a different equivalent resistance.
But just as soon as, okay.
Yeah.
And I have another question. Why don't you connect those 3 networks together and use the
like between here and these
Yeah.
positions? Yeah, you cannot because
Shouldn't they be
they
connected
are
together?
no, because RC networks are like linear networks, right? We're trying to find some RC time constant here. But if you once you put in the logic gate, that is some, you know, you have like a transconductance that you're doing there, which is some nonlinear
Yes.
function of the input voltage.
Because for wire, we connect them all together, right? And calculate
Yeah.
like for this resistance, that's all the
That's true.
capacitance afterwards.
Yeah, but a wire is purely passive, right? The wire is not an active device. So if we were to
Yes.
really do this, right, you would essentially have like a current or a voltage controlled current source here, right? Capacitance, and then this would feed into some like this voltage to ground would then generate another current that goes like that, right?
Mirror.
Yeah,
Mirror.
and that becomes more complicated now. You know, this in analog land, this is what you would do in a small signal model, as they say, right? You have like some GM, whatnot. But you know, we're doing large signal transitions, and that is not what you're concerned about. You're just concerned about the time constants that you see through each thing. And obviously, this ignores any, you know, delay intrinsic to the transistors, I guess, regardless of the load. But again, we're not concerned about that for analyzing digital delay. Okay.
I see.
Could you explain what accounts for the discrepancy between the Elmore delay and the path effort?
Like,
why aren't they exactly the same? Or something?
Well, I mean, these are all approximations. Like, I didn't do the exact calculation. What I'm showing is that to the very first order, they're almost identical. Right? It's basically 27 for each. Yeah.
All right.
Yeah, I'm like, I guess you could work out the numbers yourself and find out whether or not they're exactly the same, but they should be. Okay. All right. So let's move on. Okay, so for this, just some clarifications I think people have on Piazza about why energy drawn from power supply is like CVDD squared. So the idea is that if you have some supply VDD, right, and you charge a capacitor through some resistance, right, we know that the charge on the capacitance after it is charged fully is going to be its capacitance times VDD, right? Now, if we take the derivative of this, right, dq dt is going to be c times VDD dt, okay? So we know that the change in charge over time is just the current, okay? Now, the energy, knowing that, is going to be the integral from 0 to infinite time of the supply voltage times the current over time, right? That's basically just integrating power over to infinity. And so if we were to expand this out, this I, as we saw, is just c dv dt. So then the dt's cancel, and then you get a dv term. So what you're doing, instead of integrating from 0 to infinite time, is now you're integrating from 0 to supply voltage, okay? And then you get VDD times C times dV, right? And you can see that this is VDD times C times the integral of dV from 0 to VDD, which is just C VDD squared. Now, if you were to, charge the capacitor from some non-zero voltage V1 to a non-VDD voltage V2, you can do this calculation again, and you would get essentially C times VDD times V2 minus V1. All right. So that's the energy that's drawn from a power supply to charge a capacitor. Now, when you draw the energy away from the capacitor, right, what you're doing is you have the capacitor here, and then you're discharging it to ground through some resistance. Okay. And we know that the energy that's stored on a capacitor of a given voltage is going to be 1/2 CV squared, right? So that's the thing that you all have seen. The key thing here is that if you discharge a capacitor, let's say from like V1 to V2, the energy that you pull from it is going to be 1/2 C times the initial voltage squared minus 1/2 C times the final voltage squared. Right, and the key here is to know that when you're charging the capacitor, you are just dissipating, half the energy as heat in the resistor, and then when you discharge the capacitor, you dissipate the rest of the energy as heat in the resistor once again. Okay, so that's why the capacitor only stores half the energy that you actually draw from the power supply. Any questions? All right.
Why is the power usage 50-50 among the resistor and the capacitor?
This is sort of an intuitive explanation for that. I knew it at one point.
I'm fine with a mathematical explanation too.
Yeah, I'll have to get back to you about that. Yeah, why that's
all right.
the case. But it's probably just a function of the fact that the energy dissipated on the resistor is going to be essentially its current, right, times voltage over time. So
it's like I squared R.
Yeah, it's going to be an I squared R term, right? But then you'd have to do essentially the same calculation using I and R instead of V and I. Yeah.
Mm-hmm. Yeah, I'll think about that.
Yeah.
Harrison, do you mind explaining how the limits change again for the first?
Yeah, so if you are integrating like 0 to some, let's say t, right, and then you have something dt, right, and then this is going to be something that's dv over dt, let's say, then these cancel, and then you have to change this to a v, something that you're integrating.
Oh, I see.
Yeah. Now we know that t changes to v because we're going from 0 to vdd over the infinite amount of time. Yeah. All right. Okay. So for those of you who stuck around for the last 10 minutes of the last discussion, this was the little example that I did for energy, building upon the previous slide. So, initially we have A equals 1, C equals 1. So this is on, right? And this one is off. Out is 0. And you're trying to transition B from 1 to 0. So this goes down, which means that out charges to 1 through this path. Okay. So what is the energy pulled from the supply here? Now the final voltage at out is determined actually by this NMOS and the fact that NMOSs don't pass good 1s, right? So that means the final voltage is actually just going to be like VDD minus V threshold of the NMOS. Okay, and then from the equation before, we saw that the energy from the supply is going to be C times VDD times VDD minus V threshold N. Okay. Now, yeah. Okay. Now, how much energy is dissipated when we go from C being 1 to 0, which means that this turns on and then this one turns off, which means that we discharge the capacitor through this path, all right? Again, this is a PMOS on the top, so it doesn't pass good zeros. Therefore, our final voltage is going to be V threshold P, absolute value, okay? So that means the energy that we take is going to be 1/2, which is this is the initial energy on the capacitor, right? 1/2 C VDD minus V threshold N squared minus the final voltage, which is 1/2 C V threshold P squared. Yeah, so I went over this last discussion. Okay, hope that's the answer. So power and energy in CMOS transistors come from 3 main sources, as you learned in lecture. The first one, which is really important, is the dynamic power consumption, right? And you have this classic equation, alpha CV squared F, right? Alpha is going to be your switching activity. And this is determined based on how you configure your logic. And we'll see in an example after this that how you order your inputs can change your dynamic power consumption, right? And the dominant method of this power consumption is the fact that you're charging discharging capacitors through resistances. So exactly what we've been calculating so far, right? So the next source of energy in CMOS transistors is short circuit current, which is a direct path from power and ground, which can happen when you're transitioning the gate and the PMOS and NMOS are on simultaneously for a brief amount of time. However, this is not as important these days because the threshold voltage of deeply scaled transistors is greater than half VDD. So the idea is that if like V threshold N plus V threshold P is greater than VDD, then no short circuit current. Okay. Obviously, there will be a tiny bit because the transistors are not fully off when their gate voltages are below threshold voltage, but it is still in like subthreshold current region, which is much less than saturation current. All right. And then the last way that you dissipate energy is static power. And this is leakage, which comes from subthreshold conduction. All right. So recall from when you were learning about MOS transistors, let's say this was VGS and this was the drain current, right? That's a really bad curve. Let's say, let's go like that. All right. So VGS drain, right? If we turn this into a log scale, we'd actually see something like this, right? And in both cases, this is, let's say, the threshold voltage. So we see that below the threshold voltage, you actually do have current. And this is a exponential relationship with threshold voltage. And so even when your transistors are off, even if VGS is off, this value is actually going to be non-zero, right? As long as the drain voltage is above zero. That's the key. Okay. So the way to get rid of leakage energy is something called power gating, which means that you actually turn off the supply entirely to a section of your circuitry, or you use higher VT devices. And what that does is, if your VT is higher, then the intercept here at VGS equals 0 is lower in current. So you get, some orders of magnitude less leakage current. Okay. So as I was saying before, we have a little example of how dynamic power matters in terms of how you order your inputs into a circuit. So consider that we have this 3-input NAND gate constructed from not 2-input NAND gates, but this is an AND plus an AND, right? Okay, and the key here is that C2 is equal to C1 divided by 4, which means that C1 is larger in capacitance. And the circuit is driven with a certain frequency. And each input has a certain probability of Px, right? So you have PA, PB, and PC. So let's calculate the total power of this in terms of these parameters, okay? So the power here is going to be essentially your alpha, which is your activity factor, for the first AND gate. So let's say alpha 1 for the transition of 0 to 1 times the first capacitance, plus the alpha of your second gate, a transition from 0 to 1 of the second capacitance, let's say, okay? And then that is going to be multiplied by VDD squared times your F. So how do we find what these alphas are, right? So the alpha of the first gate going from 0 to 1 is actually equal to the probability of the inputs being 0 times the probability of the inputs being 1, right? And then the alpha of the second gate similarly is going to be this. PB, PC times PA, PB, PC. Okay. So that's how you would calculate the total power of this 3-input NAND using the probabilities where of A, B, and C being high. Okay. So if we then continue on and in this case, add some numbers here, how would we calculate the power dissipation, right? So the power dissipation resulting from this, we saw that alpha 1 would equal, I'll just give you some numbers that are pre-calculated. 1204, alpha 2 equals 0.0651, and then the power would be 5.467 milliwatts. Okay, so knowing the fact that C1 is a larger capacitance than C2, how should we reorder this given these probabilities? Does anyone have an idea of how we do this in a slightly more energy efficient way?
So isn't this like one big NAND gate? So maybe you can like rearrange the inputs and put the most frequent one going into like where C is now.
Yeah, that's right. So which one would that be?
A.
Yeah,
right?
Perfect. So you would swap these two. Okay. And what we see is that we know that based on the calculation for alpha 2, it doesn't change because it's dependent on all three. So we know that alpha 2 equals 0.0651, but alpha 1 is going to be different because now it's dependent on the probabilities of PB and PC rather than PA and PB, right? So that's going to be 1 minus PB PC times PB PC, and that so happens to be 0.09. And if you do the calculation all the way through, you'll find that the power of that is going to be 4.251 milliwatts. Okay. Does that make sense?
Yeah. So is there like a general rule for where we want to put, like how we want to arrange the inputs such that we get the smallest power dissipation then?
I think the general rule would be you want to figure out like, what the balance of the capacitances that you see are, and then put the, input that changes the most often, I guess, on the gate that would drive the least capacitance.
Okay.
Yeah. Or even
So-
more so, like if you have a chain of gates, right? You want to make sure that the one that changes the most often to be further down, I guess, the line. Therefore, it doesn't
Yeah, that makes
cause all of the rest of the stuff in the chain to switch. Yeah.
So the concept here is by swapping those two inputs, we can have lower, the first gate will have lower activity number
Yeah, that's right.
because those two inputs change less frequently.
Yeah, that's right. Because like it's an AND gate, right? So we are concerned about when this goes from a 0 to 1, and so
Yes.
the less that it has to toggle, the better, right?
Yeah.
So
see.
therefore, you want a probability of the inputs, right, being more 0 than more 1, so that the output wouldn't toggle as much. Yeah.
Because I was thinking that, like for the equation of the alpha 1, like we can use some derivative to get the optimal PB and PC, something like that.
Yeah, you definitely could. Although, like, if you were to do that, you would find that PA and PB should be 0. Then it would never switch, right?
Oh, yes.
Yeah. So.
Okay, I see. Okay, I see.
Hey, Harrison.
Yeah.
Those alphas. So you calculated the probability that P and B are off times the probability that P or A and B are both on. Is that right? That's your alpha?
Yes, that's right. That would be the probability that you are doing a switch between one and the other.
So the probability when they're both off and the probability intersected with the probability that they're both on.
Yes, that's right. Because yeah, when you do the intersection, that is defined as a switching from off to on or vice versa.
Why didn't alpha 2, when you calculated, you only did 1 minus PA PB instead of PABC?
I did for 2 ABC.
Oh, you did? Oh, I guess I missed that. Yeah. All right, my bad.
Yeah. So that would be the probability that they're all 1 or not all 1. Right. Okay. All right. So that's it for energy and power. And how much time do I have left? Oh, wow, 13 minutes. Okay, I'm going to try to blaze through some adders for this discussion. So basically, we just need to make sure that you understand the diagram, the concept of each type of adder, and also find the critical path and calculate a delay for those adders. All right. So starting off with the single bit and ripple carry adder. So the single bit is the full adder, right? Full adder that you see here. We know that in lecture that the equations that you get for the next carry is going to be this, and then the next sum is going to be A XOR B XOR C, right? And the key to remember is that generally calculating the sum is slower than calculating carry because XORs are slightly slower than ANDs and OR gates in general, okay? So when we try to calculate the critical path through, let's say, this 4-bit ripple carry adder, what we see is that you actually have a path through these carries and then out this sum, right? Because any other path you would sort of drop out earlier than this, and we know that the sum here is faster than this guy, right? And so if you want to calculate a delay through this ripple carry adder, let's say n is equal to the number of bits, right? The propagation delay through this critical path would be n minus 1 times the carry propagation delay, and then you have 1 sum propagation delay, right? And then obviously this scales with n. Okay. Another thing about ripple carry adder or adders in general is that you can build a subtractor very easily from an adder, right? So from 2's complement, we know that to negate a number, right, equals not the number, let's say +1, okay? So a negation would just be accomplished using these XOR gates, right? And then the +1 is accomplished by just putting in a carry into the very first adder in the ripple chain. That's how you build a subtractor from a n-bit adder. Okay. So the next thing that you learned in lecture was the carry bypass adder. And the key to this is that you have 3 ways of generating your carry, right? You have so-called a kill, right? You propagate and you generate. And the idea is that you kill the carry, right? You kill the carry when A and B are 0. You propagate the carry when, here, where you see A XOR B. And then you generate the carry here, right, when A and B are 1. Okay, so then you use the propagate and generate into your full adders. And then the idea is that you have a bypass path, right, which is this multiplexer here. And the bypass happens when you are propagating the input carry through all of the full adders in the chain. So you don't actually have to do the propagate through anymore, and you can just directly propagate it from here to the output, right? And so obviously that saves some amount of delay because carry doesn't have to go all the way through. So what is the critical path here? We know that the maximum amount that it can go from beginning all the way to end is you have some input here, and you go through the carrier propagation, you propagate through here, you propagate through here, propagate, and then you come out at the sum. All right? And what you also need to know here is this setup block is the block that does this calculation. So this is essentially setup. All right, so the critical path is drawn here, and the delay through this critical path is going to be, the time that it takes to go through the setup block. And then let's say, you have m bits and you have n bits in a block, and then, n bit adder, let's say. Then you would have m minus 1 of carries, right? So that's this carry propagation block here. Then you have to go through a couple muxes, okay? And that's going to be equivalent to about n over m minus 1 times the propagation delay through these muxes. So that's this guy, and this guy. And then finally, we have the carry propagation of this, which would be m minus 1, t carry, and then this sum. All right. So now you can see that this doesn't scale as much with n. It scales with n over m for the most part. Okay. Then the next thing that you learned is a carry select adder. And the key difference between this and the carry bypass adder above is that you are trying to, whoa, what did I do? Okay, the idea is that you're trying to generate both the cases where you would carry a 0 or carry a 1, right? So a critical path through this is very similar to what you saw before. You would go through this path, through these multiplexers, and then generate a sum. So if you have, input, and these are n-bit blocks, then very similar to above, the critical path delay would be, again, the setup delay plus m times carry, because you're generating the carry for all m bits. And then you have n over m muxes, and then a sum. All right. So this is exactly this, almost exactly the same delay as above, but rearranged in a slightly different way. Okay, and then the one way to decrease the delay for carry select adders is to do a so-called square root thing. And the idea is that you want to try to make the earlier stages faster than the later stages in that whole chain of multiplexers. So what you do is you allocate fewer bits at the beginning. So let's say you see that this is 2 bits, this is 3 bits, this is 4 bits, and this is 5 bits, and so on. And then, the path through here would be much faster than the path through here, for example. But you don't really care so much about the path on the right side because that would have fewer multiplexers to go through. Okay. So again, the critical path would be through here, and the propagation delay would be the setup time of that, plus m times t carry, whereas m is the first stage's number of bits. Then if you were to actually work this out, you would find that if you have p stages, that the sum of the delay through the multiplexers for this type of structure ends up being about square root of 2n. So you add square root of 2n times the mux delay, and then the sum. So you can see that the difference between this square root setup and the previous one is that you're comparing to square root of 2n versus n over m. And as long as you make the m-bit per stage to be small, then this term also becomes smaller than the previous one as well. And so this type of square root type carry select adder becomes faster than if we were to divide up the bits evenly. All right, how much time do I have? Okay, 4 minutes. So the last type of adder that is very important for this class is so-called carry look-ahead adder. The idea for this is that you are trying to break up the add operation into groups of bits where you compute a propagate and generate for each group, and then you combine the groups in a sort of tree structure, and then you generate carries at each bit position that you're concerned with, right? So an example would be a 3-bit cogstone adder, which is what we call this. And oftentimes you'll see these types of carry look-ahead adders drawn with diagrams with these like white and black squares and circles. What these represent are just logic functions with inputs on top and outputs on the bottom. And in this case, you would have like GI is going to be AI and BI, and then PI is AI XOR BI. Here you have the generating the sum, and this so happens to be the propagate XOR generate I minus 1 to 0. So you see that's a block. And this value here so happens to be the carry for that block. Then this block here is going to be G of J to I is G J plus P J G I. This one will be J P J to I is P J P I, and then this particular one is going to be the same equation as that, right? And so when you actually build this cogstone adder, you sort of work from right to left. And you start off with input carry, and you want to generate the first sum bit. So the first input carry, you're going to use this white square. And what you'll see is that you get something like C0, P0, and that gives you your first sum. Then you need to add bit A or bit 0 from A and B. So A0, B0. And then you would use the black square in this case. So you have a square like that, right? And then this outputs a G and a P, okay? And then this G and a P go into a circle. And in this case, you have a white circle because you are just generating the generate that goes into the next sum. So this would be C1, P1, and S1, okay? So P1 actually comes from here. No. Yes, should come from here. All right. Then, wait, no, that's not true. P1 should actually, what am I doing? This is a white circle. Ah, yeah, okay. So P here, yeah, this goes to here. And then the previous generate actually comes from here. Then I'm just going to work through the remaining part of this. You have the next bit. You have this, which is a black square. This comes from here. No, it comes from the generate. Say this is G and that's P. And similarly, this would go into a another circle. Let's see, that goes to there. Yes, E2, E2, S2, and then finally we have this A2, E2, E2. This comes from here. That goes, oops, nope. That comes from here. Nope. there, and C2, C2, S3. Yep, and then sorry, C3, P3. Okay, yeah. Apologies for rushing through this. I think we're going to do more adder multiplier stuff in next week's discussion. But for the most part, like when you're doing these adder problems, you would need to make sure that you know what all of these constituent blocks do, and then how you combine all the propagates and generates together in a tree structure to form the full carry look ahead adder. Okay. Yeah, with that, I'll take any questions. We are some amount of time over.